Hi. In the last example, we tried to apply a neural network to predict the behavior of epoxy-based part which is being heated in an autoclave or in an oven, in a convection oven. That's the important part. So we were varying two parameters, the thickness of the underlying metallic tool and the speed of the flow inside the convection oven, which is related to the heat transfer coefficient. And then we're trying to predict the maximum temperature that this heated epoxy is being experiencing. But what we discussed is that if you try to predict the behavior with limited data set outside of that training data set, the neural network predicts quite an incorrect behavior. So here in this section, we're trying to step-by-step improve it. So in the second approach, which there is a Python code provided for this, which is heat2.py, we're trying to use physics-informed features. So first, we need a bit of understanding of what is actually happening. What is some of the correlations here? So if you look at a case where you have extremely large tool thickness, and you're trying to cook something very tiny on top of that. This is so massive, this tool, that it becomes a massive thermal mass, which basically slows down the whole convection. If you try to heat up a part like that, you might not even get to the 180 C that you're trying to cook for in this case. So in this case, think about it this: if you have like a cast iron versus an extremely thin aluminum pan, and you're trying to cook a steak on that, it takes much longer on a cast iron to get to the temperature you want. This cast iron needs a lot of energy to get heated to that specific temperature. So that's one understanding. The thickness of the tool, as it becomes thicker and thicker and thicker, has a direct impact on the maximum temperature that part experiences. But in a case like this, when you are extremely, you have a very high, very thick tools, if you increase the transfer of energy around it, so let's say you increase the velocity a lot more, versus you increase the velocity a lot less. Obviously, it helps more as you add more of these airflows around the tool and part. So if you look at the two cases I have compared here, for an extremely thick tool, if you have very small heat transfer coefficients, you never get to the 180 C. For an extremely thick tool where you have very good airflow, you might eventually get to 180 C. This sort of implies an exponential plateauing behavior. And you can come up with exact equation. Here we are trying to say we have some understanding of the physics and we have some high-level correlations. And you can think about it with any other physical system. If you have a correlation that describes part of the physics and you know that correlation is correct. So here we say maximum part temperature for extremely thick tools has a plateau type behavior as a function of heat transfer coefficient, which means that the maximum temperature increases and eventually stables at 180 C in this given case. So if you know that type of correlation, again, if you're not familiar with the physics, that part is not important. Think about it as in a given multi-physics problem, you have some sort of close form correlation, which is not accurate, approximate, but implies an underlying truth. And what it implies is, in the region that is here, as we move away from the data points, we should plateau to constant value. That's what it implies. So instead of training the model based on the thickness and initial heat transfer coefficients, I'm training it now with the thickness and this exponential function based on the heat transfer coefficient. What this exponential function does is when the heat transfer coefficient goes large, it drops its contribution. So you are imposing something before it goes inside the neural network. What's the effect of something like that, that you modified your inputs based on some understanding of the physics? If you use this approach to predict the behavior, again, everything else is the same. You have a training zone, which the tests and trainings are done in that zone. Then you extrapolate beyond that zone. And now you can see that this area where you have, when you're in a very thick tool region, which is the thickness is around 5 centimeters, the extrapolation behavior is very good. It actually captures that extrapolation behavior. Not in the other region, because we didn't inform the neural network about the physics in the other regions. Let's go back and compare what you had. It's a subtle change, but it's actually quite effective. This is the prediction we had before. It predicts that the Tmax still goes up with a slow ramp. But in reality, it shouldn't go up. It should just plateau to a specific temperature. And that's what we inform the neural network. And this is what it also captures. When you transform your features based on that underlying correlations, it becomes very good in the area that you're trying to enforce. So the details of that in the heat2.py. And I'm not going to go into details of how to do the transformation. It's a very simple change based on the baseline code. But again, it captures one area, but it misses the other area. So you can also enforce something else on the other area. But instead of that, I'm going to use a different technique in approach 3. This approach is we call physics-informed loss. So in one area, so if you look at this initial, I'm going to look at the 2D version of the L and H. This L and H. Your initial data points are at this corner. And we kind of established that as we move away from this data into this corner, we are approaching a plateau for maximum temperature. You can kind of think that we know the sign of the derivative. The change of the Tmax with respect to H almost goes to 0. So it's like, you know that in some areas you should have almost 0 derivative. We also know a bit about the other area based on the underlying physics. Underlying physics says if you have a very thick tool, it's like you have a good heat sink, so it absorbs the heat. But when you go to the thin tools, all of a sudden it's not a good heat sink anymore. It's just resisting. It's just a heat resistance. So that again comes from our understanding of the underlying physics. So instead of absorbing heat, it doesn't do that. So as the tool becomes thinner and thinner and thinner, more energy goes into the part, less energy gets absorbed by this heat sink underlying that, and the temperature should go up. So that means that as the tool becomes thinner, the temperature goes higher, or it has a negative sign of derivative on the other side. So we have that understanding based, again, the specific example, which is heat transfer. You can think about the other examples. If you have some knowledge of what is the sign of derivative, what's the sign of the change outside of your training zone, do you know that? If you know that, you can enforce that. And we're going to enforce that using a different technique, which is physics-informed loss. I'm going to tell you how the implementation is done. Again, there's a Python code, Py3, in this case, heat3.py, and you can take a look at that. I'm going to briefly go over the details of how the coding is done. But I encourage you to run that on your own computer and look at the exact implementation. OK, so let's look at it again. We have a domain of data, which is length and heat transfer coefficient. In one corner, we have our training and test data. That is the 75 blue lines and 25 pink lines, which pink dots we are using for evaluating our accuracy. In this zone, which is a higher zone, we know that the derivative of the outcome with respect to H should go to 0. She should plateau. In this other zone, where we have the thin tools and to lose this ability as a heat sink, we should start increasing the temperature of the part with a negative derivative. So if you look at the equation for loss, in this code, we are updating the equation of the loss. There is one component which is basically the square of errors, the predictions of the neural network with respect to the given data. In every iteration, we calculate that for the training and test data provided in that corner. But we also select some points in every training outside of that zone in this new dashed area. And we look at the sign of derivative. If the sign of derivative is not negative, we're going to add a penalty factor. We're going to penalize the loss equation by saying that the derivative has to be negative. You're not getting it right. So there is a constant multiplied by all the positive derivatives in that area. And then further, we're going to select some points from this region, and we look at the sign of the derivative. We look at the derivative of data in that location with respect to heat transfer coefficient. If any of those values are non-zero, we're going to penalize the loss by summing them up again and add it to the entire loss. So in every iteration, we're trying to minimize three things. Fitting in that corner, zero derivative with respect to one of the parameters in that corner, negative derivative with respect to other parameters in another corner. And we're going to see how good it gets outside of the training zone. So the implementation is done using an approach in TensorFlow. It's called gradient tape, which basically you can calculate, easily you can calculate the derivative, any derivative of the outcome with respect to any of the incomes. And it could be first derivative, second derivative, any of those things that you want. So we have the implementation here. There's a code. Sorry, there's a function that has been provided. And the function calculates this loss that I mentioned. So first you calculate the baseline loss, which basically the mean squared error of the predictions versus the data that you have. Then in the second part, using gradient tape, you calculate the derivative with respect to one of the parameters, this with respect to column 0, which means with respect to the first parameter. And if it's non-negative, you're going to penalize that. And in the second one, you look at the second column. And if it's not 0, you penalize that. You add all of these using a lambda value, which is like a weight for these constraints. We set them equal to 1 in these cases. So effectively using this method, if you train it enough, it should capture both mean square error in one area, zero derivative in another area, negative derivative in another area. If you run the code and do the comparison, you will get this behavior. So I have to explain to you what you see here. This is, the slope might be subtle, but first of all, we are capturing this area the same as the previous approach, which was the physics-informed feature. In the other area, it might seem that the slope is constant, but if you run the code and you rotate this 3D plot, you can kind of see that the slope is slowly going up. So it's like a negative slope in the other region, in this region. But it's so subtle that if you move too far away from the data point, it doesn't capture it. So something to remember about this approach, we had a bunch of data points, and we set the derivative to be negative. And it captures the area very close to data, which is these areas. But if you move further away from data points, it's not accurate. So there is limitations about this method. Even though we are trying to enforce as much as we can, we will get a negative slope. But the sign of the negative slope goes higher and higher up. So it actually becomes more drastic as we move away, and we are not capturing it. And there's no reason for this approach to be able to capture it, because it doesn't know that this negative becomes more pronounced as we move away. So good for areas around the data points. Maybe not too good if you go way away from the data points. So we're going to go to the fourth approach, and this approach becomes the most complex approach, and I call it domain transformation, and it becomes the most successful approach, but it requires knowing a lot about the underlying physics. So you might not have this understanding about any given problem, so that limits the application of this. But if you know this, this can capture many complex scenarios with very limited data points. So the whole idea is the fact that there are two types of physics involved here. If you have a case where you have a cast iron pan inside a normal oven with a steak on it. So that's a steak on a cast iron pan. And you're heating it up, and you look at the temperature at the center of this cast iron pan. Let's say the air temperature, you set it up to go to some temperature and wait there for 2 hours for the steak to get cooked. The temperature at the center of the steak would have a lag following that. So at every point, there's a lag between them. And the reason we have the lag is the fact that it takes time for the convection and conduction to happen. So this is a balance between convection plus conduction. Remember I said there are three physics involved here? Two of the physics are here. There's a third physics which is the heat generation via polymerization, and it's not included here. So it's just two of the physics. So if you look at this curve, if you neglect one of the physics, you get this yellow temperature. If you add the heat generation, you get this other curve that is built on top of that. So this is what we're going to do. We have a lot of understanding about this physics. We have actually closed form equation even for predicting something like that. Instead of training a model to directly predict Tmax, this is what I'm going to do in this case. Getting the curve that is here. We will try to predict the difference here with a neural network. And then add it plus our understanding based on the closed form or other equations that represents here. So you split the physics in two parts. For one of them, you have some very good information. You use that. And instead of predicting the actual Tmax, let's call this T lag. You will try to train a neural network that predicts Tmax minus T lag. So neglecting one of the physics. And that I called domain transformation, because instead of predicting the original output, you're predicting a new output. So you're going to a different domain, which is guided by the underlying physics. So I'm not going to go into this part, which is the underlying physics for the simpler component, which is conduction plus convection. It's available in literature if you're interested to see. I provided the paper that we have published on this topic, actually. But the intuition behind this is given here. If you just look at the conduction and convection, which is the yellow curve here, by neglecting the polymerization, here the lag, the difference between the air temperature and the part temperature, is related to how much thermal mass you have over heat transfer coefficient. So it's not linear exactly, but is correlated to M, which is the thermal mass over H. And that's the closed form equation again if you're interested. But that's the intuition behind it. More thermal mass you have more lag. Less heat transfer coefficient you have more thermal lag. So that's what we know. The difference between the two physics, which is the maximum temperature minus this T-lag, that gap that I described, is related to how much thermal resistance you have versus how much thermal mass you have. It's the fight between two physics. One is how much the surrounding convection and part thicknesses resist the flow of energy, and the other one is that how much they need energy to get heat up to the specific point. So we know that correlation as well. So what we know now, again, reviewing it, if we decouple the physics into conduction and convection, we have a closed form equation, approximate solution for that. If you look at the difference that remains from heat generation, we know a correlation, approximate correlation over that. All of these things are related to thermal mass, thermal resistance, and heat transfer coefficient. So we're going to put all of these things together to train a new machine learning model. So this is how it's going to be done. If you get your initial data points in the corner, the closed form equation, which is T-lag, is shown here. This is the surface with the yellow label T-lag. If you look at the difference between Tmax and T-lag, we will get this new domain. So the x and y's are tool thickness and heat transfer coefficients. Instead of predicting the maximum temperature here, we are predicting the Tmax minus a closed form equation representing one of the physics, T-lag. So now we are going to train a new machine learning model, a new neural network. The output is Tmax minus T-lag, and the input is thermal resistance over thermal mass. And it's because we know this physics is correlated to this type of input. So we are additionally helping the neural network to capture the correlation. This implementation is in heat4.py. So to compare, if you look at the original neural network that we used, I'm going to go back a few slides. This is the original neural network we used to train the model. You have L and H, and you're trying to predict Tmax. In this new approach, we are changing both inputs, reducing the inputs from 2 to 1, and we are also changing the output. So that's why I call it domain transformation, because everything has changed now. R and M are related to some of the geometry parameters, but also related to the thickness of the tool, and also related to the heat transfer coefficient. The equation is provided in heat4.py, but basically what you're doing is predicting the gap between Tmax and T-lag, and then add it on top of the T-lag, and you will get these predictions now beyond the initial training zone. So few points to consider. The neural network has only seen data here. It has been only trained on the difference between the maximum temperature of the part and a closed form equation T-lag. And then beyond that point, it predicts that change and add to the baseline closed form equation. And it can capture the behavior very well on this side. On the other side, where we go to small tool thicknesses, it can capture the change in the slope without you modifying the loss. It's just simply a different approach to implement physics here. Out of the techniques that I mentioned, of course, the physics-informed features are quite simple to implement. Going back to the 4 features. The physics-informed features were very simple to implement. It's just, if you know some correlations, you can change your features based on that correlations. And it's like the baseline, the first approach that you can implement very quickly. The physics-informed loss requires you to do a bit more implementation, but can become very powerful, especially around the training zone, where you can enforce some behavior that you want. The fourth option, physics-informed domain transformation, requires you to know a lot about the underlying physics. In this case, it was heat transfer, which might not be the area that you're familiar with, but at least you can kind of see what type of familiarity you have to have with the domain. Do you have the closed form equation for part of the physics? Do you know correlations for other types of physics? You can combine all of that to do domain transformation. The last one which I'm not going to talk too much about it, and I'm not going to provide the code for you, but I'm just going to go quickly over that, is the fact that you might be able to do this in a very different approach. And I'm going to simplify it even further. If you just look at heating of a metallic tool in an oven, there are some partial differential equation governing the problem. There's convection on both sides, and there's conduction. You can solve this using a neural network. We call this physics-informed neural network. In the literature, it's very common to call it PIN. The way you're doing that is you are calculating a loss in every step based on if you're satisfying the differential equation and if you're satisfying the boundary condition at the same time. And you're minimizing this loss value step by step. Once it's done, you have satisfied all the differential equation everywhere inside the domain that you want. It's in a way solving it using a different numerical approach. We have many different methods to solve the partial differential equation. I mentioned finite difference, finite volume, finite element. In this case, you're solving differential equation with neural network. The details are provided in my paper that I have listed here. If you want to learn more, you can refer to that paper. In summary, I introduce you to different physics-informed machine learning approaches where you can take a baseline neural network, change its inputs, change its output, and change its loss function based on the underlying physics to get a much more capable neural network.